One of the most obvious places that we can look at heat transfer is when we're looking at the physical change associated with changing states of matter. So let's take a look at some phase changes and how we can examine the heat transfer associated with those changes. So first of all, just some pretty straightforward states of matter things. You've probably talked about these 15 different times in the past. But when we're talking about states of matter, what we really are looking at is the attraction between particles versus the kinetic energy of the particles. So you've probably talked about states of matter in a bunch of different ways, but this way is really looking at the energetics of what's going on. How fast are the particles moving compared to how much they want to stick together? So in a solid, the attraction between particles is relatively high compared to the kinetic energy. So in a solid, those individual particles tend to stick together. They might still move around, they vibrate a little bit, but for the most part, they are stuck together and have consistent neighbors. In a liquid, we've got attraction and kinetic energy at a little bit more similar level. So liquid particles are still attracted enough to each other that they don't just fly apart, but they're moving fast enough that their neighbors change all the time. And finally, when we've got a gas, the forces between the particles, the attraction between the particles is, relatively speaking, low compared to the kinetic energy. Now, we've got to be careful here because the attractive forces between particles doesn't really change. Right? So two particles just naturally have a certain attraction for each other. The thing that's changing here is the amount of kinetic energy and how that compares to the attraction of those particles. So when we're changing state, so if I just have a change of state, I have to add or remove energy, I have to add or remove heat, but the temperature doesn't change during that change of state. And if we think about those state changes, we can describe them as being endothermic or exothermic. Endothermic, energy or heat coming in, things like melting, which is often referred to as fusion, vaporization, boiling, or sublimation, that's when something goes directly from a solid to a gas, or exothermic phase changes, things like freezing, condensation, or deposition. And in all these cases, the opposite processes, even though they have different names, they're the exact same process, chemically speaking, right? So they've got the same magnitude of energy required. It's just that the direction of that energy changes depending whether it's endothermic or exothermic. All right, let's look at an example. How much energy is required to melt 792.38 grams of solid water initially at 0 degrees C to form liquid water at 0 degrees C? So again, we have no temperature change happening here. This is just the phase change. This is just changing from solid water to liquid water. We look at that with delta H, an enthalpy of fusion for water. The enthalpy of fusion for water is 79.9 calories per gram. So again, just like with a lot of these heat transfer problems, let's use the units to set ourselves up. So we've got 79.9 calories per gram. Well, if I want energy, I just need to get rid of grams. And I'm given grams in the problem. So 79.9 calories per gram times 792.38 grams gives me, what is this, 63,300 calories, or probably easier to convert that to kilocalories. Move the decimal 1, 2, 3 places, and we get 63.3 kilocalories. So that wasn't too bad, going from solid water to liquid water. What if we take 792.38 grams of liquid water initially at 0 degrees C and form solid water at 0 degrees C? Well, this is the same process, it's just going in the other direction and the same amount of material, so it's the same energy as before. Now, the difference here is just the direction that energy is going. Is that energy going from the system to the surroundings, or is it going from the surroundings to the system? One way we can put a bunch of these concepts together is with something usually referred to as a heating or cooling curve. So in a heating or cooling curve, we combine a whole bunch of information into one picture, but these are all separate individual little pieces of information. So keep that in mind. Keep them separate when you're working with them. Heating and cooling curve is just a way to put them all together. So this is specifically a heating curve because as we go left to right, we're adding heat. Temperature is going up. So what do we have? If I'm starting with water and it's at some temperature below 0 degrees Celsius, as I add heat, that water, that solid water, is going to warm up. That's a heat capacity problem, right? We talked about that last video. Once it gets up to 0 degrees C, now the temperature doesn't change while I go through an enthalpy of phase change process. Once I get through that, once I go through melting and all of my water is liquid, well, now I've got another heat capacity problem where I'm just heating up liquid water until I get up to the boiling point. Then I've got another enthalpy problem where I'm just adding heat to get everything from liquid to gas. And then finally, once I get up to gas, once everything is gas, once it's all boiled, now if I keep adding heat, it's another heat capacity problem. The temperature keeps going up as heat is added. All right, what about an example? The most important thing about heating and cooling curve problems is break it down into its individual problems, right? Break it down into all the bits and pieces that we go along. So how much energy is required to melt that many grams of solid water initially at negative 27.34 degrees C to form liquid water at 48.92 degrees C? So before we look at the math, let's talk through this. I've got a sample of water. It's solid, and it's at negative 27.34 degrees C. So the first thing I have to do is add heat in a heat capacity problem to get that up to 0 degrees Celsius. Once it's at 0 degrees Celsius, then I need to keep adding heat to get it through that phase change into the liquid state. And then once I'm at the liquid state, well, now I just have to increase the temperature, again in a heat capacity problem, to get me up to my final temperature of 48.92. So specific heat is solid water. Let's do the first part. This is given in the problem, calories per gram Kelvin, 0.492 calories per gram Kelvin. I know that I've got 792.38 grams. That gets rid of grams. Kelvin, remember, change in temperature, degrees Celsius and Kelvin is the same amount. So from negative 27 up to 0, here I did it formally, final minus initial. There's my temperature change. Run those through and I get 10,658.53 calories. I'm keeping way too many sig figs here because I'm in the middle of a problem, but just to keep track of that, I highlighted and made my sig fig digit orange. So if I were rounding, this is where I would round right here, but I'm not going to round quite yet. Let's do the next step. Let's do that enthalpy of fusion. So 79.9 calories per gram. I've got 792.38 grams. That gives me enthalpy of fusion for this sample is 63,311.16 calories. Again, not going to round yet, but I will keep track of where I would round. And Finally, the third step is just specific heat of liquid water from 0 up to 48.92 degrees C. That's 1 calorie per gram Kelvin. There's my amount. There's my change in temperature. 38763.23 cals, and we'll note that sig fig digit. Now, these three processes are all happening. I just have to add them together, right? So 3 little steps that I add together to get my whole problem. So adding those all together, I get 11273.2.92 calories. Let's check out those sig figs. I'm adding, so my sig fig is in what? It's the hundreds position here. It's the hundreds position here. And it's the hundreds position here. So all of these are going to round to the same place, the hundreds position, and converting that to kcal because it's a big number, I'll get 112.7 kcal is the amount of energy required to heat that water through this particular range. The most common place where people struggle with these kind of problems is trying to make everything into one big monster equation. And it's not one big monster equation, right? It's just each of the individual steps. In this case, there are 3 of them. Specific heat for solid water, enthalpy of fusion for water, and specific heat for liquid water. So do those 3 smaller steps and then just add up the amount of energy required for each step to get the total amount that you need. These rely on a number of problems that we already did, a number of types of things that we already talked about. Heating and cooling curves really is just a way of putting them together into one bigger and honestly more realistic problem. So do a little bit of practice, and I'll see you next time.